first of all, we're going to talk about the Hall probe. So the Hall probe is nothing but a retarded block of metal, right? So I've drawn a block of metal here. I hope everyone can see it. So let me tell you about this block of metal. So what we do is we put it in a circuit, but we put it into the circuit in this really weird manner, right? So I'm drawing basically a 3D version of the block of metal. So let's name the sides, or instead of naming the sides, let's give the sides colors. I felt I feel like Pablo Picasso.
Nice.
Yes, they're actually really good quality. Usually felted pens to me like 2 use korba তারপর দেখবা যে খসখসানি শুরু হয়ে গেছে.
Really?
Yeah, they're like.
This was like the only set I could find.
Well, it's really good.
I thought it would be good.
Really good. So, তারপরে like we can draw this face. This is yellow, by the way.
What side's that?
That's the back side, A side. Selector সাথে হবে A side, right? This is a little tricky now, but we'll just have to find a way. And this is the bottom side, and this is the top side. Right. So basically the top sides are orange, right? Top, bottom. And then we have the back. এটা তো আমি দেখতেছি না, ওরা কি দেখবে?
That's pretty bad.
Front. বোঝা যায়? আল্লাহ জানে. Back and front. Shabab Khan, your videos are awesome, sir. Thank you. And we have left and we have right. Right. So these are the faces. Shabab Khan make me so happy, man. Like
Really?
Your videos are awesome. Like
awesome.
And even called me sir
Videos
and
are
stuff.
awesome.
Not me.
That's all.
No man. Hey, why are you trying to hurt me? You're mean.
It's alright.
It's alright.
One day.
It's alright.
We'll get there.
Yeah. Back to physics. So we're going to be putting this in a circuit. How? We're going to connect the left and right side, basically the two blue sides, to a power supply, right? If you want, you can put your fancy rheostat and stuff and your ammeter for no good reason into this circuit. Bye. Yeah, specifically that, right? And then what you do is, this is the interesting part. You connect another circuit to the top and bottom, right? So this is basically represented by the red lines. And here we have nothing but a voltmeter, right? So this is connected to the top and bottom. So this is what we've done. And then what we do is, we allow a magnetic field to pass through the yellow faces, basically from this side to that side, like this, basically the back and the front. We have magnetic flux lines passing through it, right? Yes, into the paper, basically, like this. So this is the 3D version of what we're trying to do. So what we're going to do now is I'm going to draw a simpler 2D version to explain exactly the mechanism of what's going on. So when we create the circuit like this, basically we have current flow from these two ends, right? And we have the voltmeter connected to these two ends. And with the magnetic field enters the paper like this. So now, assuming, let's imagine for a moment, if positive charges were to enter the metal block from this side, so these are positively charged particles. So if the metal block experiences positively charged particles entering the block like this, what's going to happen is you have positive charges in a magnetic field. So the flow of this is going to lead to a force to act on the positive charge. Which way will this force act? There's an easy way to find that out. Can you tell me how, Nishlian? Hey, man.
No, I mean, definitely.
Definitely.
Yeah, O levels.
O levels.
Yeah.
This is A2 levels.
Still.
Still. Thing is thing. Thing is thing. Still, thing is thing. Alright. So yes, we use the left hand rule, right? This is my left hand. I hope there's no chocolate still stuck to it. Eto chocolate yes, chocolate খাইতে পেট ভরে গেছে.
But did you have all of them? No, fridge racks.
Fridge রাখছি সাদিয়া গুলো রাখতেছে না এতগুলো তো আর দিতে পারবো না বুঝছো ফাড়া আনসার করছে so force field current so basically if that's the case then force is what I need to find field is into the paper and current is in this direction so I'm trying to hold it like this so this is the field going into the paper and current in this direction. So the force is going to be upwards, which basically means what? The positive charges will bend upwards like this as they pass through the metal block. And if that's the case, interestingly, what's going to happen is this will cause this side to become slightly positively charged and this side to become slightly negatively charged. And that is when the voltmeter will start getting a reading. And because it starts getting a reading, this is where we can actually figure out how much that reading is. And from there, we can figure out how much the strength of the magnetic field is. So how exactly do we find the strength of the magnetic field? We do this in a known magnetic field first. The flux density is known. So like, say this is B, the flux density is a certain amount of Tesla, and we get a voltage on the voltmeter. And that basically tells us that in such a field, that's the sort of voltage you're going to get. And then what you do is, you repeat the experiment in an unknown magnetic field, and then you use the value that you get to find out the value of the voltage. All right. So this is the basic concept of the Hall probe. And the Hall probe basically has a couple of factors which leads to an equation. So what we've done today is we've asked Maqsadul to help us out with the equation. So I'll just introduce you to the equation and Maqsadul will take it from there about how to derive the equation. I'll be here, so if he says something wrong, don't worry. So the Hall voltage, basically the voltage across these two faces, VH, the voltage across these two ends, is VH is equal to BI by NTQ, right? Where basically VH is Hall voltage. This is the voltage that we're going to use to measure the magnetic field strength, the flux density. B is the flux density. I is the current passing through the metal. N is basically the charge carrier density. This is basically something you already saw in your AS exams, right? Can you tell me the equation which has charge carrier density in your AS exams, Neshlian? Nave. Okay, Nave.
NVQ.
Yes, Nagvi. I had a student named Nagvi. I miss him a little bit. All right.
Shout out.
Yeah, shout out to Nagvi. So I is equal to NAQV. So NAQV, N is charge carrier density. This is cross-sectional area. Q is charge per carrier, and V was drift velocity. And here, basically, N is the charge carrier density, is the same N. T is the thickness of the block. So if we want to show thickness here, basically this is thickness. This end here, this is thickness. And Q is basically, again, the charge carrier density. So BI by NTQ, B flux density, I current through this is going to be I, right, and VH. All right, so yes, Maqsadul?
Okay, guys, I was thrown into this situation. I'll try my best, and then Rahul
will silently judge him.
Hopefully, he can help me.
Okay.
He can help me. How about you? I tell, and then you can write. Can you do that?
Why don't you?
Should I?
Yeah. You're wasting time now.
Okay. So we have this situation.
You could like use the paper. Do you want to use your paper? He did his homework on a paper.
Yeah.
So like
so we have a situation where there's a moving charge, right? And then there are two forces that act on the charge. One is the magnetic force, and the other one is electric force. So we could use two equations to equal them, balance them, right? So EQ equals BQV.
Could you explain that, Maqsadul? What do you mean by that?
What?
Well, what did you balance?
Oh, okay. So the whole, like, if you look at the scenario where you have a moving charge in a magnetic field, it creates, like you said, this positive and net positive and net negative charge. So you have one force, which is the magnetic force acting on the charge. You also have, because of this potential difference, a electric force acting on the charge. So you could equal them here. So EQ, which is the electric force, equals BQV. V being the what's it called?
Come on.
The gear velocity?
Drift
velocity.
The equation. Drift velocity. Yes, very good.
So you could cut the charges out. E equals BV.
Fair enough.
And E, the electric force, you can write it as VH, yes, by D, that we know. D is this?
Yes.
It's D. Okay. Next, you have, we're going to work on the right side, BV. So equation of drift velocity you have here is I equals NAVQ. You can rearrange it as
Nagvi.
You can rearrange, make V the subject, and then you can put it back on this equation over here. You can put it back here. So you have VH, which is the Hall voltage, and you have BI NAVQ. you make VH the subject, you have this, and basically what you can do, and I did it in a bit of a shortcut, is you could write A by D here.
Fair enough.
Right?
Fair enough.
Right?
Yeah, yeah.
I don't know if that's going to confuse people.
No, it's all right. A by D.
Okay.
They're not so stupid.
Acha, I'm sorry. Okay, so A by D is basically your thickness that Rafa Best said is T over here, if they can see it.
Yeah, they can see it.
Okay, which is
They're not
T
blind,
over
man.
here.
They're not blind.
And you end up with this equation.
Yes, that's correct. Maksud, that was pretty good, man.
Thank you.
You're not bad at explaining stuff.
Right.
So I'll just do this. Is this for AS? No, it's not for AS. Abid, it's for A2. It's 11:22. It's for A2 stuff. All right. That's your friend. Don't laugh at your friend. Okay, I'll just quickly go through this again. Maksud did a decent job, but I'll just quickly review. So what he's basically saying is, once we have this situation going on, the voltage across this is the Hall voltage. So the Hall voltage is basically the voltage across this, which is VH, right? And what this causes is the electrons want to move up, but they can't continuously go up because there's a force which is pushing them downwards and a force which is pulling them from underneath. So this is what the potential difference builds up. So this build-up is basically an electric field, and the electric field force F is equal to EQ, and the magnetic field which is causing them to go up is F is equal to BQV. So this is what Maksud did here, EQ and BQV. So basically, if they, as a result, go straight, the cancellation of the two results in EQ is equal to BQV, cancels out the Q, E is equal to BV, and E, based on your AS stuff, is E is equal to del V by D. So the V here is basically this V, which is Hall voltage, which is VH by D. So VH by D is equal to BV. So you substituted this into this. And yes, we bring in the drift equation, which is NAQV, and then we rearrange that for V is equal to I by NAQ. You substitute that in the place of V, you get this step right here. After that, VH is equal to BID by NAQ, just rearrangement, blah, blah, blah. And A by D, area by, what was D again? Distance. Oh yes, distance between the two, up and bottom, will give us the thickness, which is in this direction. And basically the thickness does have an effect on how much the Hall voltage is, and this results in this equation, VH is equal to BI by NTQ. And that was that.
Yeah, I have a question. Where do we need this? Like, how do you use this? Why is it useful?
Well, to measure the strength of any magnetic field, actually.
Really?
Yeah. So say, for example, if this pen represented a Hall probe, all right? Or actually, we should use something a little different. Say we use this pen. So this pen is a Hall probe. So what we should do is we should always place it perpendicular to a magnetic field. So if this is the end, oh my God, it's a chabai careful, I said, Nishlian. My God, Nishlian, take it back. So
I did not do that.
I do not do it. Okay, fine, you do not do it. So we have two ends of the magnet. Basically, say a face of the magnet. The Hall probe should always be this. My finger is the Hall probe, for example. Oh my God, I don't know what I'm doing. Okay. So this is the Hall probe. So basically, you always have to hold the Hall probe perpendicular to the direction of the magnetic field, right? Because if you hold it like this, you're going to get a voltage only when the flux lines are passing perpendicular into the Hall probe. If you rotate the Hall probe, then the reading is going to be different. If you rotate it by 180 degrees, this is going to give a reading of 0, like not exactly this. If you rotate it like this, if it was like this and you rotate it like this, because now basically what you're doing is the electrons were moving up, right, which is giving you a voltage. If I rotate it like this, the electrons are now moving in this direction, right? Will that give you a Hall voltage?
I don't know what it is.
Well, if it's going in this direction, say the flux lines are entering in this direction, so you could do force field current. So force is what you need to find, field is this way, current is this way. So yeah, actually you will get a voltage.
Yeah.
But you won't get a voltage if you rotate it like this. If I take it and I tilt it like this, basically rotate it along this axis.
Right.
So that's not going to give you a Hall voltage. So a very important thing is you always have to hold it perpendicular to the flux lines. And if you take it and you completely rotate it, make it upside down, you'll get the same reading. It's just going to be negative. And if you do that, that's basically going to lead to the voltage being the same value, just in the opposite direction. So yes, that's the basic concept of the Hall voltage. It's a very important precaution that you hold the Hall probe perpendicular to the flux lines. And they do ask that what's going to happen if you rotate it like this, what's going to happen if you rotate it like this, and also what's going to happen if you rotate it by 180 degrees. That's the most common question. And what does happen? Basically, the value is the same, it just becomes negative. Thank you, Maksud. You did a fine job at deriving this. Basically, coming back here, I'm just going to quickly go into the thickness bit again.
We did some other color today.
Yes, okay. We'll use this color. So basically what he did is we had area here, which came from the drift equation right here, and we had D here, which came from this equation over here. So what these basically mean is the area would be this area, basically this side of the block, and D would be this. So basically what we have is, we're just drawing this again here, where this is D, this is the thickness, basically this, and this whole area is A. So what I did was A divided by D is equal to T. Ta-da! So we did that right here, basically A by D, and that's why we could substitute it with T. Simple as that. Alright, last thing for tonight, then I can go to sleep. We're going to talk about velocity selectors, alright? It's very similar to the Hall probe, that's why we've kept it together. So what does a Hall probe, what does a velocity selector do? Basically say we have electrons and they're traveling over a range of speeds, and that's what happens after, say, thermionic emission or photoelectric emission. Electrons are traveling in all directions with a range of speeds. Even if you accelerate it across a potential difference, all the electrons will not have the same speed. They're going to have a range of speeds. So say for some specific experiment or for some reason, we need to create a situation where the electrons all have the same speed. So what we do is we pass it through a very specific situation. We pass it in a situation where there are two fields. We have a magnetic field and an electric field. So say, I'm just making this up now. Say I turn this into a positive side and I turn this into a negative side. So this creates an electric field. Let's use blue to represent the electric field. So the electric field is going to be downwards like this. Right? So this will cause electrons to experience a force which way, Maksud? Upwards, that's right. So we have electrons moving upwards. So if we want to find the force of the electrons moving upwards, F is equal to EQ. Moving on, F is equal to EQ. And so F is equal to EQ. And on the other hand, we're going to have a magnetic field, right? So how will the magnetic field be? So magnetic field is going to be basically not in, we can't say that yet. Basically, we need a magnetic field which bends it in another direction. So we're going to use red to represent the magnetic field. The magnetic field's result should be, it should cancel out the effect of the electric field. So which way does it bend? It bends like this. So if it bends like this, what we get is basically a magnetic field where the force should be F is equal to BQV. Right? So if it's BQV, when will it go straight? When EQ, oops, this is in red, my bad. So when EQ is equal to EQV. So which way does the magnetic field have to be to cause the force to act downwards? We can use the left-hand rule, right? So here, be very careful because we're using electrons, the current is going to be in this direction, opposite to the direction of motion of the particles. So force, field, and current. So basically, the force has to be downwards, that's what we know, has to act downwards. And the field is what we don't know, and the current is going to be opposite like this. So basically, if it's downwards and if it's like this, it ends up being into the paper. So now what I can do is I can draw the crosses, where the crosses represent the magnetic field into the paper. So as the flux lines are like this into the paper, the result is that the electron wants to go up because of the electric field and wants to go down because of the magnetic field. And only at a certain velocity will the electrons travel straight. At which velocity? The velocity where EQ is equal to BQV. Oh, I should have written this in red. So now that we have our equation, it's going to bend downwards and hit this plate. And by the way, there's this little slit here which allows the electrons to exit. So if they travel too fast, it moves downwards and hits the bottom plate. If they travel too, because the magnetic field's resultant force is too high. If they travel too slow, then the magnetic field's force is too less. The electrons hit the top plate, or they move upwards, they bend up or down. So as a result, basically anything which is going too fast than your desired velocity will constantly keep moving down, and anything less than your desired velocity will constantly move up. So what we did say is basically the velocity is proportional to the electric field strength and inversely proportional to magnetic field. So yes, if they're traveling too fast, causes the magnetic field to make them bend too much, the force is too high. And if it's too slow, then the electric field is stronger than the magnetic field. And only ones with a specific velocity are the ones which can escape. And the ones which can escape are basically calculated using the equation V is equal to E by B, where E is the electric field strength and B is the magnetic flux density. And that's it, guys. This is basically the concept of the velocity selector, and that's how it goes.